Okay, so welcome everybody to another Clarify kind of lunchtime seminar. So today we have Julia Gonski, and she's talking about the LHC Olympics 2020. This is a community challenge for anomaly detection in the high energy physics community. Julia is currently a postdoc at Columbia, and I believe you did your undergrad at Harvard University and has worked on a number of beyond standard model analyses. So please take it away, Julia.
Great. Yeah, I did grad school at Harvard, so that's close enough.
Grad school, not
I was there. Yeah. Great. Okay. Thanks so much, Isabel, for having me here, and for all of you for joining today. So my name is Julia Gonski. I am a postdoc at Columbia, as Isabel said. I work on the Atlas experiment, but that's not exactly the subject of what I want to talk about today. This is a bit more of a zoomed out perspective on a sort of broad community challenge that we call the LHC Olympics 2020. And this is really focused on anomaly detection, so applications of different anomaly detection methods and how we can use them to our advantage in the search for new physics at high energies. And so the quick outline of my talk today, I'll start with the sort of physics story of this anomaly detection pursuit. So a really quick overview of the standard model, why and how we are looking for new physics beyond the standard model. And then, of course, since the subject of this competition was anomaly detection, I'll motivate that a little bit in the context of the sort of searches that we already are doing and how we might expand our program to really make sure that we're covering all the possible areas of phase space where new physics could be hiding. And then, of course, I'll talk about the LHC Olympics itself. So an overview of what exactly this is, what were the different techniques that were competing, what were all the technical details of the data sets that were folded into this competition. And then there were actually two installations of the competition, one in winter of 2020 and then one in the summer. And so I'll talk about the differences between each one and the results that came out of those, and then wrap all up with conclusions from the competition itself, but then kind of zooming out a little bit and looking at the role of anomaly detection going from these simulated sorts of competitions and how we could extrapolate that to actual searches with LHC datasets. So the first things first will be the physics motivation. And so that starts with what I would call the standard model situation, which is that we do have a model that we like very much, which is the standard model you can see in this nice table on the bottom left here. This is a quantum field theory that describes all the known fundamental particles, which are each of the entries in this table, and their interactions with one another, the fundamental forces. And the reason we like this so much as physicists is that it has been very predictive and very confirmed experimentally for a long period of time. So for the past several decades, we have this nice sort of relationship with the standard model where it makes a prediction of a particle that should exist that we can then build an experiment and observe in data to some high precision that allows us to make a discovery of that particle. And the most recent and maybe the most notable example of this was the discovery of the Higgs boson in 2012. This was the last predicted particle of the standard model. And so it was discovered at the Large Hadron Collider with sort of great fanfare. It won the Nobel Prize for this discovery. And the kind of underline, the point that I'm trying to kind of sew into this whole story is the relationship between theory and experiment that I think has been really prominent in the way that we look for new physics up until this point, that we have really strong theory, a really great mathematical foundation in the standard model, and that can turn into good experimental results. So you have this kind of feedback loop where the theory can make a prediction that we can look for in experiment and then use that to kind of feed back into how we can make the model better and how we can expand it. But of course, this isn't the full story. Otherwise, we wouldn't be having this conversation at all. There are a lot of notable things that are missing from the standard model that I'm sure people are familiar with, but I would really just list a couple of these that I think are maybe notable, again, from the experimental perspective, things that we have observed or that we can sort of recognize in data, but that don't fit into the model itself. So there is no standard model candidate for dark matter, no explanation of neutrino mass, which was a subject of another recent Nobel Prize for the discovery of neutrino oscillations, which confirmed the need for neutrino mass in standard model, which is not currently contained in the theory. No explanation of matter-antimatter asymmetry, and very notably, no particle explanation for gravity. So gravity is not a fundamental force that is included in this model. And that, again, has been sort of brought to kind of the forefront of people's minds with the recent Nobel Prize for the discovery of gravitational waves by the LIGO experiment. So again, sort of using kind of the experimental lens to point out a lot of these observations and data that we don't have a model prediction or a model way to understand them. And so this is kind of sets up an interesting scenario. And obviously a lot of us have been doing a lot of work to try to resolve some of these discrepancies. There are a lot of really excellent, elegant, robust theories that extend the standard model in such a way that we can resolve these remaining mysteries. And then on the experimental side, we've been busy hunting those down in the actual data. Right now, the Large Hadron Collider is our sort of big main experiment for that. And so that's the main source of these, but this has been going on for quite a while. And since 2012, since the discovery of the Higgs, there has been no conclusive discovery evidence for new physics, which means we can't really point to any of those, all these multiple theories and say, okay, this one is definitely the roadmap. We can use this to find new things. And so there are, you can kind of speculate about why it is that we haven't found new physics, but something that you could pretty conclusively say is that these processes are rare. If they were very common, we're at the point where we're looking for processes that are increasingly rare. Otherwise, we would have seen them more frequently. We have quite a bit of luminosity now with the Large Hadron Collider, and that makes the problem all the more difficult when you're looking for really a needle in a haystack kind of situation. And so there are so many of these theories that it's kind of difficult to really explain all the different predictions of them. But I do want to take, just as an example to illustrate a point, one of these theories, supersymmetry, and talk about sort of the snapshot of where we're at when it comes to testing that theory in the data. And the way that I'll do that is with this plot on the left here, which is the summary exclusion for the STOP, the supersymmetric top quark. Supersymmetry as a theory just gives each standard model particle a partner. And so the STOP quark is the supersymmetric partner of the top. And the way to interpret this is that we have on the x-axis, we have the mass of that STOP particle, and then on the y-axis, the mass of the lightest supersymmetric particle. So these are particles that should exist in the theory, but their masses are a free parameter, and so they could be anywhere until we make an observation. And anywhere there is shaded area on this curve is a place where, to 95% confidence, that particular signal hypothesis has been excluded. So for a particular STOP mass and a particular LSP mass, this exclusion goes up to kind of the edge of this colored curve here, which is just about 1.25 TeV. And so this is, this limit has been getting kind of further and further out to higher and higher masses since the gray curve, I think, covers the exclusion as of 2012 or something. And so this might be a bit concerning for a couple different reasons. One, if we get much higher than TeV scale for some of these new particles, we lose some of the elegance of these theories. A lot of the elegance comes from cancellation of fine-tuning sorts of parameters that will kind of fade away if these particles get much heavier. But in addition, we only have a machine that has a certain center of mass energy. So above a certain mass range, we won't even be able to produce these particles with our current experiment. So this is a bit upsetting when it comes to looking for new physics, that some of these really key SUSY candidates are excluded up to TeV masses. But there's a bit of a catch in this whole story. It's a little bit less pessimistic than maybe it will seem, which is that these exclusions are extremely model dependent. So if I want to exclude one area on this plot, not only do I need to make assumptions about the masses of these two particles, but I may have to fold in other assumptions about the mass hierarchy of the other supersymmetric particles, the decay modes of that STOP particle, its branching ratios to those decay modes. And all of that means that when we say these are excluded, it's really quite a specific statement. And I think that this is a real blind spot in our current search program, that many of our searches are motivated in this way, where we make all these assumptions based on the model and use that to define the region of data where we look. And it kind of sets up this notion that there may be new physics, new particles, sitting in events that we just haven't looked at yet because they have eluded the scope of what these models can predict. And so that's kind of a bit of foreshadowing to where the whole idea of doing more model independent searches comes in as a way to supplement the way that we already have a search program built on these really important theories. And so I'll talk now about the experiment itself, where we can do all of this fun testing and probing, which is the Large Hadron Collider. This is a 27-kilometer proton collider sitting underground across the French-Swiss border that collides protons at a center of mass energy of 13 TeV. And then it collides them at a couple different points around this accelerator, but I'll emphasize two in particular, since they're sort of especially relevant to the LHC Olympics story. So the two general purpose, multi-purpose detectors are ATLAS and CMS. They are across the ring from one another. And the purpose of these detectors is to encircle those collision points and collect as much data as we can about what happens after that proton collision event. And so you can see in these sort of cartoons that these detectors are multi-layered as well. And if you look a little bit closer, you can see that the sort of reason for that is that we can synthesize information across different detector subsystems to uniquely identify possible particles that could be produced in that collision. And not only can we identify those particles, but we can obtain really important information about them like their location of the detector, their energy, and then use that in sort of forensics effort to piece together what happened in that proton collision. And again, if we're looking for these really rare processes of new particles being produced in these collisions, the goal would be to identify one of those really rare events where something interesting happened that is then evident in the decay byproducts. And so I'll talk a bit about the data sets, since we are kind of looking at this through a bit of a machine learning data analysis sort of lens. The core of what data comes out of those detectors are low-level signals from not only each one of those detector subsystems, but each one of these cells, sort of the individual quanta of those detectors. And the demonstration that I can give for this is this little picture on the left. So this is an image of all of the different cells in the Atlas calorimeter. So the detector itself is cylindrical, but this is sort of an unfolded view. So you can see the eta and phi dimensions of the detector on the X and Y axes here. And then the Z axis on this image is the magnitude of energy that cell observed. So if a particle passes through those cells, it deposits a certain amount of energy through interaction with that material. And the reaction of that detector component is proportional to the amount of energy that it saw. And you can see a sort of feature that's very prominent in this picture, where a bunch of neighboring cells have particularly high energy deposit rates. And so this is a nice way to demonstrate that because this is data that's coming from some underlying object, that these cells are the signals in each one of these cells is all quite correlated in that spatially or in other sorts of ways, these signals can be linked to some underlying process. And then to give a magnitude of the amount of data that we have, for each event, there can be order thousands of particles that pass through the detector in some way. And we have something like 100 million channels in the detector that we actually are reading out. So it's quite a lot of data at this very, very low level, and almost can be sort of overwhelming if we just wanted to use that. And so what we do is kind of go up to higher levels of abstraction. So the next level will be to take all those detector signals, like compiling them across those different subsystems, and turn them into physics objects. And so that would be something like any of the particles in the standard model, a muon or a photon, or a jet, which is sort of a hadronic clustering of particles that turns into a sort of cone-like shape. And in this cartoon image of a top anti-top production, you can see how one single proton collision event can turn into a bunch of different objects. And we can reconstruct these through the signals that they leave in our detector. And then we can go one level higher than that in terms of abstraction, and go up to event level sorts of variables. So one of the really prominent ones is something like missing energy, which comes from particles that leave the detector that don't leave a signal. And we can just compute that through momentum imbalance in momentum conservation in the initial versus final state of the event. And things like the delta phi between different objects in the event that can give information about the spin of the particles that were produced in the initial collision. And so again, because these are all coming from some underlying process, these high-level event variables can also be quite correlated. And so this is what, just a quick example of what this looks like in real life. This is a real event display from the Atlas experiment. So you're looking here at 3 different views of the Atlas detector in the different kind of corners of the picture here. So this event was a real Higgs candidate, where the Higgs decayed to a muon, a neutrino, and 2 jets. And I can point out those different particles in the detector and how they leave different signals in a way that allows us to identify them. So the muon prominently is detected through these signals in the very outer edges of the detector, this muon spectrometer that is the outermost ring. The neutrino that gets produced in this decay doesn't interact with the detector at all. And so that just gets reconstructed in this momentum imbalance missing energy calculation that I just mentioned in the previous slide. And then last, these jets, which I want to spend a bit of time on because they also are a sort of a relevant ingredient of the LHC Olympics story. So this is kind of piecing together tracks in the inner detector of various individual particles. But because of confinement, something like any kind of colored particle, like a quark or a gluon, doesn't exist alone in the detector. When it is produced in this collision, it hadronizes, so it kind of showers in energy in such a way that it builds this cone type of shape that also links to energy deposits in the calorimeter cells. And you can piece all these things together and cluster them in this sort of cone shape. And these are, with a Hadron Collider, these are a very common phenomenon and one of the really key places where we can be looking for new physics. So with that kind of theory background and the experimental background, I'll get into the actual question of anomaly detection. And to kind of preface the whole idea of anomaly detection, I'll first just start with maybe the more vanilla version of machine learning that we do use very frequently in the LHC, which is supervised learning. This is something that's been in play in analyses and in reconstruction, and even at the trigger level in the LHC for years and years. And this is just specifically because we have a really robust way to simulate these proton collision events. And so we have a lot of data sets available to do labeled training, supervised learning sort of thing. And as I mentioned, this data set is really high stat, it's complex, and it has a lot of correlated features. And that means that these, even just for a classifier sort of problem, this is a particularly great data set to be taking advantage of with these sorts of algorithms. We really see this nice boost in performance when you have a method that can take advantage of all the subtle correlations that are present in the elements of the data set that you train over. And so I'll give a quick example of this, which is just a simple neural net that is used to classify boosted Higgs bosons from typical backgrounds that are predicted in the standard model. So things like QCD or top processes. And the way that this works in the LHC is that we just train over labeled data sets. So we have simulated Higgs particles, simulated background processes. We train a multi-class classifier, and we get this nice neural net output score where you can see our signal is well separated from both of those sources of background. And then we turn that sort of naturally into this ROC kind of interpretation where for a particular value of Higgs efficiency on this output discriminant, we know exactly what kind of background rejection we can get. And the way that this gets kind of swept into the whole idea of searching for new physics is that we have now, through this process, a metric that we can use to select specific events from our whole set of events that we produce at the machine that are enriched in a process that is interesting to us. So in this case, if we're interested in studying the Higgs, we want a sample that is very pure in the Higgs. And so we can build a classifier that will reject events that are not the Higgs and enrich ourselves in events that are. And so that's all well and good if you know exactly what you're looking for. So in order to have that classifier that picks out this process of interest, I need to know what the process of interest is. And so there's a, if we kind of bring it back in this idea of model independence, there is a bit of a place where that assumption can fall apart, which is that there's a possibility that we do not know the characteristics of our signal. In this whole story of searching for new physics, where we are using the theories to motivate what we're looking for experimentally, we may be missing things that we did not predict. We sort of require a prediction, a description of a signal model, a particular signal hypothesis to do this typical search pattern. And so the idea of anomaly detection would be to expand ourselves to being sensitive to any kind of physics that is not in the standard model and perhaps not even be predicted by us as physicists. And so that's not to say that we just kind of blanket look at every single event and try to look for anomalies across the entire data set. We still, at this stage in development, want to make some general categorizations, but to do them in a clever kind of way. And the example that I'll give of sort of a generalization that doesn't restrict us to a signal model is that we can look for any kind of new physics that is sort of two-jet resonant. And so the general diagram in this mysterious question mark sort of formalism is that we have some new particle, some resonant thing that decays to two other new particles, known particles. It's not especially important. But what this means is that when I reconstruct, if these both decay hadronically to these jets, then I can recompute the mass of that resonant thing by computing the invariant mass of my two final state jets. And the reason that this is a particularly valuable generalization to make is that I know that this MJJ, the invariant mass of those two jets, has a smoothly falling shape in the standard model. But if I have some resonance that is unknown in the standard model, it will present as this sort of peak that maybe I can distinguish on top of my smoothly falling background. And so the goal here is that we now have this variable. I've made no other assumptions about what the particles are in this model. I didn't make assumptions about what their masses were, whether they were charged, what their spins are, if they have leptonic decays. All I've said is I expect to have some resonant two-jet sort of decay mode. And that means that I have this variable mres that becomes very valuable because I can sweep through values of it. And as I sweep through values of this variable, I can vary the amount of signal and the amount of background that I have, and hopefully find one area of that variable where my signal is enriched enough for me to make some confident observation of it. And so that's really the general structure of this particular type of anomaly detection, a lot of anomaly detection that's happening in the experiment right now. And so that brings me to the generic way that I would describe how this is happening at the LHC at the moment. And there are a couple different definitions for anomaly detection that are in use at the moment, but the one that I'll take for the sake of kind of illustrating this story is that we're trying to identify features of the data that are inconsistent with a background only model. So all we're relying on is our knowledge of what that background only process is with no signal hypothesis attached to this. And so maybe the most kind of pure way of doing that would be completely unsupervised learning, where we just train over unlabeled events. So something like training directly over data, where you don't know what kind of process was present in the data with complete confidence. This is a task that is sort of traditionally done by autoencoders. So the idea here is that if I know very well what the majority of my collisions at the LHC look like, I can use that knowledge to identify any sort of collision that is exceptionally different or anomalous in some type of way, just based on that knowledge of the background. But this doesn't have to be the only way that we do general sorts of anomaly detection. We can incorporate also other methods that have some reliance on labels. So there's a bit of a knowledge of the signal that you're looking for, but still not completely supervised classification. So for example, weakly supervised classification, where you have labels, but they are noisy. So instead of just the typical classification problem where you have all of your signals labeled as ones and all your backgrounds labeled as zeros, maybe your population labeled as ones is mostly signal events, but has some background events. And that just kind of trips up your net as it's training. It makes this task a little bit trickier. And in the context of looking for new physics, we can use this sort of premise to take advantage of regions of phase space where we know that new physics does not exist, or rather that we also know the amount relatively of the signal in the background, and then leverage that understanding of some other area of phase space onto a new one where you do suspect there may be a signal. And if there are differences between your predictions of the background in both of those places, that could be evidence of the presence of an anomaly. And then there is also semi-supervised learning, where you do have labels, but only for some events. And you can kind of mix and match all of these different categories of learning together, depending on the task that you want to accomplish. And so with this kind of notion of how this will come into play with data analysis at the LHC, we need, of course, really good tools to do all of this. So if we can motivate ourselves, we say, okay, there's a place for this in our data analysis at the moment, but how, what are the tools that are dominant in each one of these categories? How do we tweak them to solve our particular sorts of problems? And that really is where the whole concept of the LHC Olympics comes into play. So that brings me to my second section here, where we'll talk about the LHC Olympics itself. And so this isn't the first time that we've done something like an LHC Olympics kind of competition. There is a historical context through several workshops that were held in the mid-2000s that were called the LHC Olympics competitions. And so this was pre-LHC turning on, pre-Higgs discovery. Everybody was really excited about all of the SUSY and dark matter and all the things that were going to come out of the data when we turned on the LHC. And so again, this was sort of a chance for theorists and experimentalists across different collaborations to take a step back and kind of look at the search program through a broad lens. So is the search program that we have sensitive to all of the possible new physics that we are interested in? And so this was revived in 2020 by Gregor, Ben, and David, and sort of with the same notion. Now we're in a bit of a different scenario. It's been 10 years essentially since the Higgs discovery, and we've been looking and haven't found any strong evidence for new physics yet. And so it's another good chance to take a step back and kind of reevaluate the coverage of the search program that we are undertaking right now as high energy experimentalists. And so the particular focus here was on this whole notion of model independence and anomaly detection, sort of exactly because the models so far haven't turned into evidence of new physics. And also kind of coming hand in hand with the knowledge that a lot of groups were starting to investigate these kind of techniques. And it might be nice to have a real apples to apples way to compare them, to learn from one another, and to study them in some sort of simplified environment, not just going straight to the data that has all kinds of complexities in it. So the spirit of the competition was to take all of the current anomaly detection and particle physics techniques and run them over these unknown black box simulated data sets. So these were data sets that were completely unlabeled. They had some amount of background, some amount of signal. The signal was unknown, and it was just a chance to see what these different methods could discover when sort of set loose on the same exact set of events. And so I'll start by talking about what those data sets actually were, what was provided to us as the Olympians, the competitors. And so each data set was given as a list of proton-proton collision simulated events. Each event was described by a list of up to 700 particle 3 vectors. So just the momentum and position of that particle in the detector. These events were generated and showered with Pythia and then sent through a very simple Delphi's detector simulation. So basic smearing that would come from something like a detector signal, but no pileup or any other kinds of complexities that come with our proper LHC simulation. And then there were 4 such data sets that were given as part of the competition. The first of them was the R&D data set. This was composed of completely labeled signal and background events. So the background was just regular QCD multi-jet sorts of processes. And then the signal was the exact kind of topology that I had showed just a couple slides ago, where you have some large your large R jet resonance. So you have some Z prime particle that is produced. You can see in the Feynman diagram on the right here. It decays to 2 new particles, Y and X. And then because of the sort of heavy mass of the Z, these Y and X are boosted, and what they decay to, these final state quarks, are reconstructed each as a single large radius jet. So our final state is just those 2 jets, and it allows us to do this summing of the invariant mass of those jets, where we have this prominent feature that is present at that Z prime mass. And so again, this is that really important variable where we can move to different areas of this variable in MJJ, sweeping through, and have different amounts of signal and background in each one of those bins. And so that was kind of the way that we could take some of our methods and see how, if they were capable on this scenario where we were labeled, we could very easily check that the things were working correctly. But then the real competition came in with the black boxes. So 3 of these were released. They were the exact same data sets in the same format, but they were completely unlabeled data. So no knowledge of what the signal was, no knowledge of if there was a signal, and even more complicated than that, we were told up front that the particle and detector level simulation varied from data set to data set. So that the type of background, the background model that we train with or that we develop with in the R&D data set would be different than the background model that's actually present in your search area, in what would be called your data in this context. And that's a really important feature because we know that this is the exact scenario we have to face in real life, which is that our Monte Carlo simulations, especially for multi-jet processes that are dominated by tricky QCD parameters, have these known mismodelings with the data. And it's sort of a reminder that having any type of background model dependence is sort of punished in this scenario, that you really want a method that can learn very well what the background is just based on background events and not be tied in particular to any sort of background model. And that's really what we're after when it comes to completely model independent generic anomaly detection. And so I will mention also that all of these data sets are publicly available on Zenodo. They are unblinded, which I guess maybe is, if you click on it now, it'll be a bit of a spoiler alert because we haven't unblinded them in the story yet. But they are really great data sets for just practicing with different methods. I've used them myself, trying out even different things since the competition. So I just would encourage people to take a look at those if you're looking for some generic data set like this to try out a method with. And so now that comes to the competition itself and the contestants, or the different methods that were used to try to find these mystery signals in the black boxes. There were 18 teams in total, which I think is quite a significant number and really a very wide spread of different tactics that were tried. So I've grouped them here into those 3 types of learning that I mentioned a couple of slides ago: unsupervised, weakly supervised, and semi-supervised. I, unfortunately, just in the scope of this, in the time that we have here, can't go into all of them, but I will highlight a couple of them in particular from each one of those categories. So I'll start by highlighting examples from each of these 3 categories, and then I'll talk about what the best results that some of these methods got on the actual black boxes. So I'll start with the unsupervised picture. So as a reminder, this is where a learning method where your input events have no labels. So all you do is train over a set of events that you assume to be your background, and then you look subsequently on future events for any type of event that has a very low probability of belonging to that background distribution. And I mentioned autoencoders are sort of the industry standard for this sort of work. So the general structure of the autoencoder would be to start from some low-level description of your data with input characteristics that you as the designer would choose. You have an encoder step of this that would then distill all of the salient information from whatever input description you have into a lower dimensional latent space that you would hope sort of houses your key descriptive features of that input data set. And then you can verify how good of a job that encoding process did by having a decoder step, which will try to reproduce the original high dimensionality input from that latent space. And we can very easily use the reconstruction error of that reproduced input to the actual input to make this this encoder develop a more descriptive latent space as it trains. And so there are a couple modifications to this that allow us to do different sorts of things with autoencoders. A variational autoencoder has a Gaussian latent space, so you can map to a vector in latent space instead of just particular points in dimensionality. And then a variational RNN is a RNN that has an autoencoder at each time step, and you can condition your autoencoder and your development of your latent space based on the previous hidden state in the RNN. And the idea of having the RNN here is that we can have variable length inputs in whatever we want to describe as our input. So in the context of looking for new physics, and in particular for this dijet resonance kind of search, on jets, the way that we can describe a jet would be through the 4 vectors of its constituents. So these individual particles that come together in that cone shape. And then we can also stitch together some high-level variables that are computed analytically from information in the jet. So things like D2 or KT splitting that are related to energy correlator functions among those constituents. But really what we're trying to capture with all that information is to understand the energy deposition pattern in that cone of the background, and therefore be sensitive to any kind of anomalous energy deposition pattern, or what we would call substructure in a jet. And so I've illustrated this kind of in cartoons at the bottom here, where any typical QCD multi-jet process that you reconstruct as a large R jet will be sort of homogeneously distributed in energy. All the constituents will be even throughout that cone. But if you had some particle upstream in your large R jet, for example, some heavy resonance that decays to 2 things, you may be able to disentangle a sort of anomalous relationship or a number of prongs in that large R jet just by looking into these exact variables, this sort of description of the jet. And so the idea of the autoencoder would be to very well describe this homogeneous energy deposition pattern in a way that allows you to evaluate on something that has a number of prongs or substructure in it and accumulate all of those events at the tail. And then we can use this just like any other classifier where you make a selection on this score over a large number of events or jets and try to enrich yourself in anomalous kinds of events, and hopefully from there be able to identify what the new physics was in your process. So I'll move next to an example of the weakly supervised scenario. So this is, as a reminder, where the input events have labels, but the labels are noisy. So some of them might be a little bit fake. And that makes the classification problem somewhat tougher. And a really elegant example of this is the koala method that has been really propagating pretty quickly in the past couple of years. The idea behind the koala method is that you have 2 separate samples where you don't a priori know the fraction of signal or background in either of those 2 samples, except for that you know that that fraction is different. And then you force labels onto both of those samples. You impose them yourself. So in one of my samples, I call all of them 0. And in the other sample, I call all of them 1. And I train my classifier just as normal. And the only thing that that classifier can use to distinguish between my 2 mixed samples would be the features that distinguish the signal from the background events. So this classifier would then become quite adept, actually, at distinguishing between your 2 different processes of interest, between your signal and background. And so taking this tactic and mapping it onto our dijet resonance story with the LHC Olympics signal, a really nice way to have those different populations of signal and background would be to use different bins of this MJJ variable, because I know that my signal will be really enhanced in one region. And so I can train classifiers on the side bands where there is less signal, versus the signal region, a particular bin of MJJ, where I expect to have this resonant enrichment feature. And then I can use that classifier evaluated on new data to separate actually my signal from my background. Okay, and then the last category are the semi-supervised learning methods, where the input events are partially labeled. And because you have some signal labels that actually correspond to actual signal that you know at truth level, that means that you do have some description of the signal that is known. And the example from the LHC Olympics that I'll discuss here is the quasi-anomalous knowledge space, or the QUAC method. So that the acronyms do get quite fun in the anomaly detection arena. And so this actually this combines some element of completely unsupervised learning with a VAE with a supervised learning method. So the first step is to use the autoencoder, like I was just saying a couple slides ago, to give a latent space description of event features. So you feed a bunch of events and you ask the VAE to categorize them into this latent space. And then once you have those categories, you can go back and kind of peek at the truth labels to see which of those categories is enriched in which type of event, which label of event. And so here in 2 dimensions, you can see as an example where you may have in your loss space some area that is enriched in background events, some area that is enriched in real signal, and maybe even some area that is enriched in something that is not signal but is also not background. And this is particularly valuable because we know that when we start with complete unsupervised learning, we can pick up anomalies that are not new physics, but rather just detector malfunctions or noise bursts or any other kind of fluke that can come up in the data. And so once you have these categories built in your latent space, you can take your labels and train a supervised classifier to distinguish those latent space categorizations from one another and use that information to make selections on the events that you think should correspond to your genuine signal. Okay, so that's just a quick, illustrative example of some of those techniques for each of those categories. And so now we'll get into the first actual workshop of the LHC Olympics, which took place in winter 2020. This coincided with the ML for Jets workshop at NYU. And I included this photo because it was, I think, maybe the last thing that any of us did in person for a really long time. So this was a really nice chance to actually get together and talk about some of these things. And of the 3 black boxes that we were given in the very beginning, only the first one was unblinded in January 2020. That was black box 1. The signal in the end in black box 1 was 834 events with the same topology as the R&D data set. So you have some resonant particle that decays to 2 new particles. And then you have this final state of these 2 large arc jets. So this really was a bit of a softball. Like we had the R&D data set to see if we could figure out this exact signal topology. Are we model independent enough to apply that technique and find the exact same signal topology? And they left us hanging on black boxes 2 and 3 and said that they would unblind them at some future point. And so the organizers were very sort of politically disinclined to rank all of the different competitors. Some of them certainly were closer than others, but there were 2 that really stood out as sort of the gold medalists that really did a great job on finding that first black box 1 signal. The first of those is conditional density estimation for anomaly detection. This was actually done by a bunch of folks, cosmologists, which was sort of a fun experience to see how cosmologists were interfacing with this collider data. And is a nice way to see how we can take wisdom from other fields and cross-pollinate our ideas in that way. So the idea of the GIS technique is to use a normalizing flow CDE to construct a local overdensity anomaly score for a particular observable. And it relies again on this MJJ variable that we know has different amounts of signal as we go to different areas of that variable. So you start by calculating your signal probability density estimation using jet masses and the substructure variables. And then you can wiggle around in that MJJ variable to some other area of that variable where you expect to have less signal and more background. And that gives you your background probability density estimation. And then the ratio of signal to background becomes your anomaly score. So if your signal really represents sort of an overdensity of your background with respect to your background model, that can indicate the presence of an anomaly. And you can see that very clearly in their sort of money plot from their study, sweeping through MJJ and that alpha overdensity on the y-axis, and how you see this real enhancement of the overdensity right at 3.8 TeV, which is the mass of that resonant particle. And it was a similar situation with the tag and train method, which is one of these that combines different inspiration from the unsupervised learning and the weakly supervised koala method. And so the order of operations here from some folks at Johns Hopkins, the first step is that this method does require the signal events to have 2 anomalous objects. In the case of the black box 1 signal, that worked because you had those 2 new particles going into your 2-pronged jets in the final state. And so you start with the unsupervised learning side of things. So you take one of the objects in the event and you train an unsupervised classifier to give you a set of events that are mostly background-like, the majority of the events, and maybe some that are signal-like, some that are kind of exceptionally deviating from that background-only model. And so then you take the signal-like events from that unsupervised learning effort, and you train a classifier for the second object using the koala method. So exactly this way of having a signal-enriched region and a background-enriched region in MJJ, except for that you already are using the fact that the autoencoder said that event was likely to have an anomalous object 1. And so then you can do that exact same loop for the first object. So you reverse the orders of that. You end up with 2 classifiers that have cut on both of those objects. And then you can just cut on both of those classifier scores on both objects to enrich yourself in your signal process. And that method similarly led them to have this really nice kind of prominent excess in the data right at 3 TeV, the mass of the resonant particle in MJJ. So these were the really, really exceptional cases that just pinpointed this signal straight away with no knowledge of the signal hypothesis, which I think is really remarkable and very exciting to think about where this could go in an interval search. So then 6 months went by. The other groups that did not have such luck with the first black box went back to their institutions to kind of lick their wounds and gather resources and try to think about how to make things better. So there was this chance for us to kind of improve our methods in the meantime and wait for the remaining 2 black boxes to be unblinded. And that happened in July of 2020 at the virtual only anomaly detection mini workshop. And this is where things got a little fun, things became unexpected. So in black box 2, there was nothing. There was no signal at all. This was just a background model. And I think this was a really valuable addition to the whole competition because it gives you some sense of how important your background model is, but also the pitfalls of these sorts of methods. When we're doing totally unsupervised learning, the presence of fake signals is something that can certainly happen for a variety of reasons, and that is a really good thing to look out for because that could really derail our search program if that happens in data. So it's good to be robust against things like that. And then black box 3 was a fairly complicated signal. There were actually 2 different decay modes, these 2 different Feynman diagrams that you can see on the right here. And without finding both, the signal was not significant. So if you only found one of these Feynman diagrams, you wouldn't have had enough events to make any kind of clear statement about what these processes were. And as a result of that trickery, none of the competitors actually found this, although the same sort of thing happened as with black box 2, where there were some fake signals that were reported. And so I'll go to the summary results here on page 31. The organizers made these nice kind of summary plots for a bunch of different of the methods that were tried and the predictions that they were able to make for black box 1. So the mass of the parent particle, the Z prime, the mass of the 2 daughter particles that decayed into these large arc jets, and then the number of signal events that were actually observed. And this kind of gives you a sense of the spread of options ranging about 4,000 GeV in different candidates here in the resonance mass. So this was tricky, and I think we all kind of knew it would be tricky going into it, but that there was really a lot to be learned just from trying something like this out. And again, there's no such nice summary plot because black box 2 is empty and no one reported the right signal in black box 3, but that this black box 1 was really the sort of canonical way to compare these different methods against one another. And this all turned into an LHCO community paper. Like I said, this has been a real whirlwind of different results here. So if any of those methods seem interesting to people, each one of the teams submitted their own kind of write-up of their strategy and the method itself in this community paper that came out in the archive in the beginning of this year. So all the information that I don't have time to give is well documented somewhere if people want to take a look. So that brings me to my conclusions and the sort of zoomed out view of where all of this is headed based on this competition. And if you're all not completely weary of my Olympics parallels throughout this talk, this quote was in the white paper. The important thing in life is not to triumph, but to compete, which is from the founder of the International Olympic Committee. And this quote is just I feel like it's so hilariously relevant to particle physics research that it seems like it would be unfair to leave it out, that we really are just not even necessarily working for discovery, but just to be looking at the data and seeing what is actually the reality of particle physics at the fundamental level. And so I took some kind of snippets from that white paper from each of the individual teams' conclusions just to highlight what I thought were some interesting trends about people who did participate in this process. The LHCO challenge shows the potential of this method, but also its limits. This idea of having false positives in the data is something that should be, I think, somewhat of a high level of concern when it comes to these methods. I think that's maybe a bit of the sociological resistance to fully sweeping anomaly detection into our search program so far is understanding, even if you can build a method that works very well, understanding what it has told you and contextualizing that in the context of physics and the experiment itself, I think is really important. I think there were also a lot of comments on the background estimation, how important that is, your background model, your level of dependence on your background model, understanding just how dependent your background model is on a particular data set are all really important features. One of the quotes is that in the absence of a good background model, the neural nets themselves cannot achieve good anomaly detection performance. So this is really a a prerequisite for using this in the analysis context. And also the sculpting of variables. When we have a bunch of variables that we're using to select interesting events for that are all strongly correlated to one another, we can change the shapes of those variables as we select on a variable that we think is unrelated, but maybe we need to be a little bit more careful about those correlations, as I said. And so this was also the mention of a global decorrelation strategy. So in particular, in the example of MJJ sculpting, I think that's likely where a lot of these fake signals came up, is that background distribution was sculpted in different bins of your anomaly score or whatever your method is as you select closer to your signal region. And that sculpting can look like a signal enrichment. And that's something that I think we should be very careful of. But all in all, the LHC Olympics was a very enriching experience, and we hope to repeat this experience next year. So I think that the more, these sort of toy simulated data sets that we have to work with, the faster we will be able to develop these methods in that sort of simplistic regime. But so with that in mind, I also want to just contextualize what would be the steps to taking these methods from that simplistic regime to real life analysis. And one of the points we have to, I think, consider are the limitations of the simulation itself. The real data can be very, very different from the simulation for a variety of reasons. One is these known mismodelings in QCD simulation. This is a diagram of what some of these QCD processes at the LHC look like, and all of the math that has to be very carefully accounted for in order to produce realistic Monte Carlo simulation. And in particular, these non-perturbative effects can really present as weirdnesses in the simulation in certain areas of phase space. So we can't rely so directly on QCD simulation in that regard. And even moving past this simplified Delphi's detector simulation can be a challenge. I've personally have started to take some of these methods and put them in real Atlas simulation, and the picture can be really, really different. And so I think that's something that we would also have to understand. It's another one of these background model dependence things that we have to account for. So I think that extrapolating these tools and using them in real LHC simulation and data, of course, that's the goal, but that will be a whole thing on top of having the method that works at the Delphi's level. And there are some really cool methods that are coming out to morph the simulation to data more effectively that actually use these premises of anomaly detection. So simulation assisted methods that look for the differences between simulation and data as if those were anomalies, and then leverage that against making your simulation better match your data. So that's just an example of another way that these techniques can be used to improve our search prospects in general. But without maybe I'll land on the sort of the positive note here, which is that there have already been some examples of migrating this to proper data analyses that have been published and have been very successful. And I'll mention two from each experiment. So on the CMS side, the weakly supervised koala method was used actually not to identify an anomalous signal, but to distinguish multi-jet from TT bar background in a data-driven way. So not having to rely on those multi-jet simulations that can be sort of difficult, but using directly the shape of those multi-jet backgrounds in the data. And then on the Atlas experiment, the very first search analysis with the koala method came out with this dijet resonant search, this canonical example that I've been talking about this whole time. And you can see an example of the exclusion that came out of that koala paper, where the y-axis here is the upper limit on the cross-section of this process. The black is what was achieved in the koala paper, and then the red is what was achieved in the regular vanilla dijet version of the analysis. And you can see just how much more sensitive we can be with some of these anomaly detection methods. So not only are we sensitive to things we didn't predict, but also that we can actually outperform some of our traditional methods. So I think that this is really exciting and encouraging, and I know that there are a lot more methods in both experiments in the works. And so I think then the last thing that we'd have to sort of consider using this in a real analysis is that even if we can get these methods into an analysis and get an exclusion on a generic process like A to B, C, how do we bring that back to the model framework? Going all the way back to this idea of experimental theory feedback, we want all of these results to be relevant from a theory standpoint. We want to be excluding phase space for particular models and informing the theory side of development as well. And I think that that is also something that we will have to kind of contend with as these models become more relevant, and something that we should not kind of forget about as we hope to incorporate these more in physics searches in the future. So that brings me to my conclusion. I think that this is, I'm personally very excited about these anomaly detection strategies in general. I think there's been a lot of rapid development, even in the past couple of years, of using these in collider experiments. And I think that the collider experiment frontier is just the beginning. I think a lot of high-energy experiments can hope to be incorporating some of these methods as well, and are well motivated for all of the new physics reasons that I mentioned. and that this 2020 LHC Olympics experience was really, really awesome and really fun to have this kind of playground to just try out random different ideas and have these really generic data sets to work with. And there are a lot of future efforts underway. We're already starting to see this coming out in real LHC publications, and I think that will only become increasingly a factor in the next couple of years. And so I'd like to end with just a really, really big thanks to the LHC Olympics organizers for 2020 and everyone who participated, who gave us all this really great material to look at and discuss. So thanks.
Thank you very much, Julia, for this really nice, clear, and comprehensive talk. Yeah. Do we have any questions? Please feel free to use the raise hand feature, or I suppose we don't, are supposed to speak up as well. So I have a question. I suppose at this github.io, we could try out some of these things by ourselves. Is that the case?
Yeah, so that is the website. You can definitely find the data sets there. The individual techniques are all at sort of a different level of making this completely available for people to try. I think in the white paper, a lot of these individual techniques wrote their own papers on this data and had the chance to expand a lot more on these techniques. And a lot of them do come with Python packages, which I can say also because I've poked around at some of them myself. So they may not all be on that GitHub page, but there are a lot of other Git repository links if you kind of dot around for the references and things. So yeah.
Hi, I had a question, if it's okay. I don't know if I should raise my hand. Or...
Yeah, please go ahead.
Okay, yeah, that was a fantastic talk. Thank you. I was just curious about, well, I mean, I really appreciate this point at the end about, model independent is kind of, it's good in some sense, but if you can't actually interpret it in the context of a model, then you're missing something. And so, I had some discussions about trying to get these anomaly detection workflows incorporated into like the workflow systems that we're using, so you could do something like recast and actually be able to reinterpret, sorry about the noise, these searches. I'm just kind of curious, like we also had some efforts about trying with one of these other like machine learning, comparison studies to try to get the teams, instead of just providing packages, like start to actually integrate their like solutions or whatever into some kind of workflow, so that we could start to actually, I don't know, build out some of that. I'm just curious if you have a sense of if there's an opportunity in the future as this, continues to try to like put some effort into getting the different detection strategies like integrated into some of these workflow engines and starting to do like the benchmarking instead of doing it by hand, having it a little bit more automated. If that would be like a good path towards trying to get to, to where we could actually reinterpret them.
Yeah, that is a big question. I mean, I think that's a lot of definitely very relevant points. Especially, trying to ground this all in the realism of the barriers that come with using this in proper publications. It's sort of inherent in the idea of having model independent searches is that you will start to have a lot more overlap. I mean, we already know that with our defined model searches, there is overlap. There are shared final states from, and you interpret in two different theories and people do completely separate analyses. And I guess that's kind of the premise of recast in general. And so I think in that koala paper, in the weekly supervised atlas search that came out, they do compare to, I think that plot was just one of the summary ones, but there are comparisons to a lot of other searches as well to show where that overlap is. I think that we, with these tools, as they become, they're not really standardized enough yet to fold them necessarily cleanly into something like this framework. But I think that we've kind of gone through this process already with BDTs and neural nets. Like we have some standard kind of way to understand what it has learned, verify, cross-check from different areas of phase space. And I think that we could hopefully move to something like that, where there are some kind of clear requirements for what your tool has to be able to do and show, and that will help when it comes to the recasting. Like the more we can kind of harmonize our tools and harmonize our phase space across different searches, I think that would be maybe the first kind of underpinning to working everything together into one interpretive kind of flow.
Yeah, I guess I'm curious if, in terms of there's the ordering of like a technical part and then the kind of sociological part, and the one way is to sort of try to get everyone on base like sociologically, and then later we try to build this thing out technically. it could be that maybe the other way around actually makes sense, is to like try to build this technical infrastructure for being able to do it, and maybe that will actually streamline the whole process of trying to refine our understanding and getting community buy-in and things. But yeah, I'm mainly curious about your just impression of the community.
Yeah. I mean, I will say that I've been kind of in discussion on the Atlas side with. I mean, I think that this example of weekly supervised learning is a really important one. I think that has, that was the first time that there was a sort of not completely supervised learning that came out in one of these experiments, and that was a very simple version that was really just to kind of test the waters of it. I think moving to unsupervised learning, I don't even know that we know what makes us nervous about that well enough to characterize exactly what would be the process of introducing it. But I am hopeful that at least maybe we start, with just jets and just jet level unsupervised techniques, and we validate all over the place. And the nice thing about anomaly detection is that we have anomalies in the data. We have, for example, top processes in certain selections. We can verify that these things work in data, which I guess would be maybe the most important thing to developing some confidence that you were actually sensitive to some new signal and not just some detector effect. So yeah, I think, sociologically the rollout would have to be slow. But I am interested in what you say that, whether we do the technical part first and you make that, develop the tools themselves and then integrate them, or have some master integration way kind of top down that everything has to fit into. I think that's probably something that we all have to just keep in mind in the next couple of years.
Thanks.
Okay, any other questions?
Yes, I have one.
Go ahead.
Thanks, Julia, for this really nice talk. Yeah, I wanted to ask, I'm really interested in how you defined actually the different signal boxes, or the different boxes. There was, I think it was number 3 was defined in having a signal in 2 modes, but without finding both, the signal not being significant. I was curious about this statement because in order to have significance, you need some kind of assumed efficiency and therefore signal to noise, presumably, right? So how is significance quantified in that case, especially when you're talking about a rare signal, which is subdominant?
Yeah, I think maybe I used the term a bit too technically for what I actually meant. It was more just that I mean, maybe there was a sort of a technical estimate, but I may not remember the exact details. But the point was that the number of events in each one of these processes was small enough where, I mean, I guess, yeah, you're right. Depending on how exactly you went about building your signal region and therefore informing your signal to noise or your signal to background ratio. But more just the point that there were very few events in each one of these processes. But yeah, I guess it's hard to quantitatively say without also having, as you say, some lens of some analysis strategy to look through. But yeah, the statement is just that it was generically quite a bit trickier than the hundreds of events in the previous one.
Thank you.
Yeah, I actually have a question as well. So thanks a lot, Julia, for the talk. So I'm wondering, on the same slide, you mentioned that a lot of teams reported a fake signal, even though there was nothing in black box 2. So, I mean, if this is such a common pitfall, first of all, I'm wondering, are there any teams that reported nothing? And second of all, what is the strategy for just generally validating that, if you find something, it's really there for this type of method?
Yeah, that's a great question. And I think, yes, a very important one that I think that people, if we go back to the kind of sociological aspects of this, when we try to develop confidence in bringing some new method like this, we need to be very confident that we are getting what we think we're getting and that we're not getting other kinds of things. So there were some teams that did report there was nothing there. I think a lot of teams also for Black Box 3 reported that there was nothing there. I think that the best way to approach this as it comes to integrating this into real searches would be the example that I gave, to use this on real anomalies. So places where you don't have labels on each event, but that we know with basic physics principles that in a particular region, we expect a certain amount of enrichment in a certain process and predominantly some other process. So I use top as an example of that just because if you have a boosted top decay, you have a 3-pronged jet. And I've personally mostly been focused on the jet side of this. And I think that a lot of these techniques are really focused also on jet substructure sorts of efforts. And so I think there is sort of a robust way to test this, training on the data and looking for known physics processes and verifying that A, we can find that process in some other area of phase space, B, that we don't find anything else, like other sorts of detector things or sculpting and things like that. And then maybe even C, that we can take that exact same model, take it to a different area of phase space and kind of rinse and repeat. So I think that, yeah, at the first stage, there will be a lot of kind of cross-validation in different regions, but I think that that's something that we are able to do just because of the sort of spread of things that we have in our data set that we call background only. But of course, we can pick and choose what we want to be signaled depending on the region that we selected.
Okay, any other questions? We're a little bit past 2 p.m., so I think probably we'll leave it there. But I actually feel I have a few questions to email you about, but this was a really nice presentation. We really appreciate it.
Great, thanks so much. Yeah, it was great to talk to you guys.
Cool, thank you so much. And yeah, we'll be posting it online. Anything else, Peter, that I forgot to say?
No, thank you, Julia. That was a really excellent and informative talk.
Great, thank you.
Okay, thank you so much.
All right,
Bye.
thank you. Bye-bye.
Bye, guys.
Bye.